All right, always draw it, okay? And of course you got 5 and you got what, 3 and you got 4 meters and it's hanging here and I'm going to draw the mass and it's 4,500 newtons. Now let me do this, and this is what I should have done to start with. All right, the question is, and I do this on the video from yesterday, we got a 4,500 newton weight hangs from the cables. What is the tension in the 3 meter cable? All right, now look. When you do these kinds of problems, I know they give you letters, and sometimes they might put, instead of saying 3 meters, they might give you the angles right here, okay? Well, that's the same difference. This is what I do, all right? T1, T2, T3, tension in 1, 2, and 3. So right out of the gate, we see that T3, we know what T3 is, y'all, 4,500 newtons, okay? But we've got 2 unknowns. We don't know this one, and we don't know that one either, okay? It wants us to find T1, 3 meter, okay? Now again, I'm not going to do the trig functions. You can do the trig, but you do the trig, and we get these angles, what, 53.1 degrees, all right, 36.9 right here, okay? All right, now, so we've drawn it, we've done our free body. There's one thing I haven't, 2 things I haven't done yet. Coordinate system, you need to assign X and Y. You need to put that on there. Now, why did I choose right here as my origin? That's right, that's where all your forces come together. Absolutely. One other thing I haven't done, I have not determined, is this at equilibrium or is it accelerating? Equilibrium. So the sum of the forces is equal to 0. Y'all, I'm telling you, that's the most, besides drawing it, that's probably the second most important thing you got to do. Actually, probably the first, because could you do it without a drawing? Yeah, but you don't need to, okay, because you'll make a mistake. I mean, everybody's prone to error, okay? All right, so we got to sum up our forces, y'all. The sum of the forces in the X, and so let's do all 3 X equations. All right, now let's assign angles first. All right, if this angle's 36.1, then that means geometry says this one's 36.1. All right, this one right here is 53.1, so that means this angle right here is 53.1. So I've got to find this angle, and 180 minus 53.1 is 126.9 degrees, right? Did I say it wrong? No, look, let me show you. Yeah, I'm talking about this angle right here. Now we're going from the positive x-axis counterclockwise to that vector right there.
I'm talking about the angle we get from.
This one here? Yeah, that one is 36.1. Is it 36? Oh, I'm sorry, 36.9. I'm sorry. Thank you. 36.9. There we go. All right. Again, geometry tells us what? That these angles are congruent, right? These angles are congruent, okay? Subtract 180, you get 126.9. We got one more angle to do. Which one is that? That one right there. This one right here. And it's what? This angle is 270 degrees, right? From here all the way back around, 270. Okay, so now let's sum up our forces. We've got 3 variables, 2 unknowns. Okay, so let's do the sum of the forces. So we got T1 cosine of what? 126.9 degrees plus T2 cosine of what? 36.9 degrees plus T3, and I'll go ahead and write it. In T3, I really don't need to write T3. I need to write the value for T3. It's 4,500 newtons times what? Cosine of 270. Well, you know what that's going to be. Is equal to 0, right? Everybody agree with what I'm doing? All right, now watch. Now let's do it for the y direction. Sum of the forces in the y. Well, y'all look, it's the same thing except it's sine. You do sine 126.9 degrees. All right, and that's plus T2 sine of 36.9 degrees plus 4,500 sine of 270 degrees is equal to 0, right? Okay. Any questions how I got that? We're summing up Our forces here. Now, before we go any further, let me ask you something. What are the forces in the x direction going to be right there at that gathering point? They're going to be the same, but what? Opposite direction. So in other words, they cancel out, don't they? I think someone asked Monday, well, whoa, what about the forces? And I didn't stress that. They cancel each other out because when we work this, we're going to work it for f of y. Okay? Because look, and another reason, why are we going to use this equation here in a minute when we substitute everything into? Because it has all three forces. You follow me? It has all three. Well, you say, well, the top one does too. Yeah, but it's 0. This one here is 0. See, that right there is 0. Cosine of 270 is 0. Okay? All right. So they cancel out. Now, all right. Now we got to do some substitution. So we want to solve what? For T1. So to solve T1, to find the tension in the 3-meter cable T1, we've got to do what? Solve it in place of T2. In other words, we say this. All right, now let's take this equation right here. Watch. And we're going to say T1, the cosine of 126.9 is what? Negative 0.6, yeah. Negative 0.6, right? Plus the cosine of 36.9 is what? 0.799, so T2, 0.799. I probably should have written the number first. Plus 0 is equal to 0. All right, now, solve for T2. Solve for T2. All right, what does that mean I've got to do? I got to bring T1 to the other side or subtract both sides by T2, right? All right, let's subtract both sides by T2. And so we wind up with what? Negative 0.6 T1 is equal to negative 0.799 T2. Right? And then we say what? T2 is equal to 0.6 divided by 0.799, and that's equal to 0.75. Whoa, T1. 0.75 T1. All right, so let me go back up here and write that. T2 is equal to 0.75 T1. All right? You with me?
Yeah, the way we done it the last time, we had it flopped over.
Yeah.
0.799 divided by negative.
Okay, that would be to solve for T2.
Yeah.
You solve it in place of T1.
Yeah.
So you could do it that way. You could do it that way, but we got our signs wrong too.
Right.
We got our signs wrong, yeah. And I should have just,
I think that's where,
yeah.
that's where it comes from.
Okay, yeah, big time. Excuse me. All right, now can we work it from there? Look, we take this one, sum of the forces is equal to, all right, let's see, our y equation is what? Let's see, T2 was what? 0.6, and T2 was 0.75 T1 plus 0.799 T1 minus 4,500 is equal to 0. Now, where did I get that? Watch. Right here, Fy. Okay? Son of a gun, did I plug that in the right place? Yeah. Okay? All right. All right, when you do the math, what does this come out to right here? Is it 0.45? That is 0.45 T1 plus 0.799 T1. Now I'm going to go ahead and add 4,500 to both sides. Can I do that? And y'all not freak out on me? You know what I'm doing, don't you? And that is newtons, of course. All right? No. Now this is, go back right here. Okay, what is the sine of 126.9? 0. No, right here. Right there. You plug in wherever T2 is, that's what you plug in for T2. Okay? See right here? Whatever T2 is. Okay, what's the sine of 36? Did I do it backwards? 36.9.
No, so what I'm saying is that when we plugged it back in, I think you plugged it back into T1, that's that was T1 is 0.6, and then you go 0.6, and then I guess it's
Okay. Sine of 36.9 is 0.6. This was T2 right here. Sine of 36.9 is 0.6. All right, look, go back. Watch. Right here. Right there. I just moved it to the front. I just moved it to the front. I'm sorry. I just moved it. Okay. And why did I do that? Because that's what we're manipulating. You don't have to. I just did it. Okay. Sorry about that. Okay. Then you come out with what? What does that come out to equal? 0.45. Is that 1.25 T1? 1.25 T1 is equal to 4,500 newtons, and T1 is equal to what? 3,600. Is that right? Close enough? Everybody agree? All right, now let me ask you this. Now that's T1. Can I find T2? Yeah. All right, look. How do I do that? Can I go back right here and do it? Yeah. All right, let me show you. We've already found we did T2 is equal to 0.75 T1. Okay? Well, how do I find T2? Okay, well, what did we get for T1? Yeah. So that'd be what? 3,600 times what? 0.75? 2,700? Everybody concur? Now, I could ask you on an exam to give me both of them, but I may just do one. But it's easy to do. See, once you determine what you're going to substitute, what that is, then you've got, see, that's an equation. You've got it. Okay? All right. Any questions on that? Okay. It's just simultaneous. I mean, it's just substitution. Yeah. Yeah. Mm-hmm. Yeah. Sorry about that. Yeah. Okay. All right. Good. Now look, no matter what I ask you, they're going to work the same. I mean, I could put a bird cage, I could put a street sign, I could put a street light, you know. The only way it would change is if there were three. In other words, if I did something like this. And no, let me see if I can draw it a little better than that. If there were angles, in other words, one wasn't 270. Like if you had something. You see what I'm saying? That's the only, you know, where it wasn't 270, because you'd put your right there. You see what I'm saying? And so all you would have to do on your force, though, whatever, if this one had a force on it, you just, whatever that angle is, okay? All right. Okay, any questions? All right, do you want me to work one of those, number 5 or number 6? Were y'all able to do those, or Newton third law problems? Either one of them? I'm trying to think which one might be a little harder. They're both about equal. Which did y'all recommend me do? Number 6 or number 6 is a little harder because you got two different forces. Not that, it's really not harder, but a little more involved. That's the word I probably should use. I shouldn't say hard. Okay, 6. All right, let's look at number 6. Okay, you got a horizontal surface on which it is frictionless. That makes it easier. And so we draw our boxes here. And then we got a what? A 2 kilogram one. And so we got a 1 kilogram, a 3 kilogram, and a what? A 2 kilogram box. And you've got a force being applied here, force here, and you've got a force being applied there, 6 newtons. Okay? We want to know what force is right there. It says B on C. Right? B on C, correct? Okay? All right, where's our axis going to be? Right there, right? Okay? Now we've drawn it, the free body. Well, we haven't really added in weight. We know weight is which way on all of these?
Can I ask a question?
Yeah.
What would your axis be between the next two?
Okay.
Would it be the same?
Yeah. Just as far as your axes go.
Okay.
Now the force wouldn't be the same. The force here wouldn't be the same. But as far as the axes go, yeah.
Okay.
Vertical, horizontal. Okay. All right, and then of course you have a normal force, F of N. You have normal force. But what is the normal force equal to? It's mg, right? Weight. Okay, all right. This one's easy because it's flat. Angle, a little different. All right, got to add in sine, cosine. Okay? All right. One other thing we haven't determined. What is it? Okay, it's sliding. And notice you've got different forces here. Oh, it tells us if Fn, that was 18 newtons. I'm sorry. I left that off. Y'all should have called my hand. All right. Is this going to be accelerating? You got an 18 newton force pushing this way, and you got a 6 newton force pushing this way. Which one's going to have the net force? 18. Vectors. Remember vectors? Adding vectors? Okay. So it is what? If there's a net force, it's what? Accelerating. Okay. Now, did you see the steps I went? But we haven't punched a calculator yet. We're not going to till we get all that established. You got to. You got to draw it, label it. Now, I added in a little more than we probably could have added in. I added in the weight and the normal force. You need to know that, though. Okay. Notice you do draw your arrows, label everything. That's a force of 6 newtons. I should have put is equal to F. And if you want to label it F1, F2, okay. FA, FB. All right. Okay? All right. So the sum of the forces then is equal to MA, right? Okay. Let me ask you something. What is the net force in this problem? How much is it? All right. You say, well, yeah, but what about all them blocks? Well, okay, what are those blocks doing? Are all those blocks moving at the same speed, same acceleration? They're touching, even if they were hooked with cables or rods or whatever. All right, let's see. Are they? That's why I got these blocks in here the other day. I just didn't get to it. Well, are they? Let's see. And let's just say that's going to be my 6 Newton force. Okay. Yeah. Okay. So we don't worry about those yet. So what's my net force? 18 this way, but 6 is what? 12. Very good. 12 newtons. So the net force is 12 newtons, right? Okay. So we've established that. We've established they're all accelerating at the same acceleration, right? Acceleration is the same for all three. Okay, y'all, can we find then the acceleration? Huh? Yes, net. Thank you. Okay. Has to be, yeah. So we got 1 kilogram plus 3 kilograms, gummit, plus what? Plus 2, which is 6. And 12 divided by 6 is 2 meters per second squared, right? Yeah. Okay. Okay, now, I'm going to show you how to work this thing in part by part, how to find this, okay? And there's more than one way you could do this, but I want you to understand the reasoning behind all the arithmetic, okay? All right, we know that what? We know that Newton's law says F of 1 on 2 is equal to the negative F of 2 on 1, right? Okay. All right. All right, so there's an 18 Newton force. I'm going to start from the left and go to the right. Okay. All right. So we've got an 18 Newton force that is moving to the right, correct? So we've got 18 newtons. All right, now, now notice the mass of that box. What is the net force of that box? Just the box. Up. Right? How'd you get that, Ms. Shields? Look, if there's an 18 Newton force pushing in this direction, the mass of that box is 1 kilogram. It's accelerating at 2 meters per second squared. Okay? But since it has there's an opposing force right here, then what will be my net force? 16 newtons. Okay? So we got 16 newtons net right here. All right, now this box is pushing on this box with a force of what? Well, how do we find that? Well, what do we start with? Well, we got 16 newtons right here. 16 newtons, net force. All right, what's the mass of that box? 3 kilograms times what? 2 meters per second squared is equal to what? 10 newtons. So the 3 kilogram box has a net force of 10 newtons. And so at point B on C, what is the force that B is applying on C? I did label them A, B, C, didn't I? Then B on C is 10 newtons. All right? You want me to prove it to you? Watch now. Well, I don't think you're doing that right, okay? It doesn't look right. Well, yeah, it is. It doesn't look, but it is, okay? Because, look, it can't have, the force of each block cannot have any more than what its mass will allow it to have, because they all three have the same acceleration, okay? All right, now watch. All right, so if there's a 10 Newton force right here, 10 Newton force, all right, then what's the net force going to be on C? All right, 10 newtons, now watch, minus what? 2 kilograms times 2 meters per second squared is equal to 6 newtons. Hey, well, wait a minute. So in other words, This box is going to have a 6 Newton force, and how many newtons do we have pushed against it? 6.
So is it always going to work out like that?
Mm-hmm. That's one way you can work it. We could actually do a little more complex equation and cancel a bunch of stuff out and have one calculation, but I like to show you this way, even though it's a little longer, because look, Newton's third law works. I just proved it to you. This one has 6. Well, look, I got 6 is going this way, 6 is going back that way. So he's right. Okay? Okay? Now there, again, we could work it another way and cancel. Nah, I don't do that. Okay? Because it kind of leaves out, to me, it leaves it out because you think, well, okay. But here you work it all out and you see it. Okay? All right. Okay. So we verified Newton's third law. Now look, 5 is pretty much the same way, except you got ropes or chains or bars or whatever you want to call those things. It's not going to change anything. Yeah, but isn't that rope elastic? Yeah, well, yeah, but not that much. Okay. Does the rope have tensile strength? Yes. Will it break? Yes, if you exceed it. But smart people, when they're doing stuff, and they know the tensile strength, they're not going to exceed it because they don't want it to break. Okay. And does it stretch a little bit? Does it stretch? Yeah, but not enough in this situation to make that big of a difference. Now, if it was a bungee cord, oh, heck yeah. You know, oh yeah. Yeah, your tension's going to be, that's called rheostasis, by the way, where your tension is changing. There's a lab we can actually do. Someone had an old professor email me one where we actually calculate the rheostasis of a rubber band. Because if you stretch a rubber band and let it go, it doesn't go back to its original spot. It never does. It gets close. That's why they eventually break. You know, you keep using it, it eventually breaks. Why? Because of rheostasis. Okay? So elastic stuff, okay. It's a pretty neat little lab. I thought about doing it, but I hadn't yet. But anyway, it's a neat little lab. Rheostasis. We can't do everything. All right. Okay? All right, so you should be able to do number 5 now. Number 5, pretty much the same way. What about an incline problem? Or do you want to look at chapter problems? We got time for one more. Now, y'all, I'm serious. Monday, y'all are going to work problems. I might work one, then I'll come around and help some of you, but I don't. Some of you get up here and work them. At least 2 or 3 people. At least 2. Okay? Number 9. I knew everybody would want that one. Okay. That's a good one. Okay. That one's frictionless. We got to do some with friction eventually. Frictionless is easy. Friction, you have to add in friction, of course. You add one more equation to the entire equation. All right, so you got a surface that's inclined. What was that, number 9? I'm going to do it like that. And so we got a box here, and then we got a box here. Is that right? Actually, that one's bigger. Ah, shoot. Well, whatever. Try it again. Number 9. All right, it's incline. And it's being pulled upwards, right? And notice the mass, this is 2 kilograms, and this is what, 3 kilograms? Actually, it should have been longer. Anyway. And it's accelerating. Uh-oh. All right. And the acceleration is what? 1.3 meters per second squared. What is the force in newtons? So we want to find F. Okay. Okay. All right. So we've drawn it. Let's determine the sum of the forces. Is it at equilibrium or is it accelerating? All right. Now let's draw our free body. We know we got normal force this way, don't we, on both of them? All right, so what is, all right, now look, we got to complete this. Remember that the normal force is perpendicular to the surface. So we got to do this right here. But now wait a minute, which way does gravity pull? Straight down. Label it mg, mg. Okay. Huh. Mm-hmm. Okay. All right.
It's also at an angle of 30 degrees.
Oh yeah, thank you. That is, I'm just going to say theta. Theta is 30 degrees. Okay. All right, y'all. Let's sum up the forces in the y direction. Oh yeah. Whoop. Where's our axis? So in other words, perpendicular to the incline is y. The part of the incline is x, but it's at an angle, right? Okay. All right, so the sum of the forces in the y are what? Well, we've got the normal force. Watch now. Is the normal force. All right, which direction is mg? All right, let me ask you something. What is that angle right there and right there? 30 degrees. Okay. All right. But now remember, on a flat surface, the normal force is what? But y'all, it's not on a flat surface. So what vector do I look at? All right. We know that gravity pulls straight down, but according to our definition of normal force, that's it. So what is adjacent over hypotenuse? Adjacent over hypotenuse. Cosine. Yeah, there we go. Hey, it's Wednesday. That's all right. It's hump day. All right. All right, now, is it in the positive or negative direction? Look at your coordinates. Negative. And it's cosine, right? Theta. You with me? All right, now hang on a minute. We did not assign and sum of forces in the y direction. We know it's accelerating in the x, but what about the y? Let me say x. What about sum of the forces in the y? Is it going down into the incline plane or jumping up off the incline plane? Is it moving up and down on the incline plane in the y direction? In the y direction? Nope.
Because of the coordinate system.
Because of the coordinate system. See, you got to establish that coordinate system. So that would be equal to what? 0, right? Okay. So we could actually define it this way, couldn't we? We could actually say, well, let me hang on. All right. Time. All right. Okay. All right, now what about the sum of the forces in the x direction? Well, we've got the force. Remember, that's the force we're looking at. All right, now, since gravity is pulling down always, but it's at an angle. So what vector, some of you probably wonder why I draw those others there, what vector arrow coincides with the effect of gravity pulling on the box? All right, which way is the box going to slide? Is it going to go this way or is it going to go this way? All right, it's sliding this way, isn't it? So which vector here coincides with the effect of gravity because it's at an angle? Right here. Right there. Because remember, it's pulling at an angle. It's not going to go straight down in the incline at a 90 degree. It's at an angle. Well, what trig function is opposite over hypotenuse? Watch. Opposite that way over hypotenuse. Sine. Right? Is equal to what? MA. Did somebody say MA? Very good. All right, well, let's look at why, though. We know that it's accelerating up the incline, and up is in positive what? X direction. So it has to be positive because it's going up. What if it's going down? Okay. Well, in actuality, what we could do is just make both signs. We could make, but now let me ask you something. Which way is gravity pulling it? Down. So in actuality, you could just make them both negative or make them both positive, because you know what happens when you divide by negatives. It cancels out, right? Okay. All right. So just remember that. Okay. That's why you got to put that coordinate system on there. All right. Okay. So. All right. So let me ask you something then. Is the f of y going to have any influence on this motion? No. Because it's what? It's an equilibrium, but also it is frictionless. When do we use the normal force? What is frictional force? Mu of S what? Times the normal force. Is there any friction? No. So, can you now find force? Huh? Does that make sense?
Do we not use the 0.20 that's stated in the problem? What is that?
Oh my God, this one has friction. I was thinking it was frictionless. I'm sorry. Son of a gun. I was looking at my notes. All right, this one does have friction. Son of a gun. Okay. So the friction, it does have friction. Yes, we will. All right, now let's do this. Let's add this step to it. All right, everything stays the same, except now we got to do what? That's 0 point, and that's kinetic. 0.2, thank you. Sorry about that. Okay. All right, so now we do have friction, so we're going to do what? We got to add in one more equation, don't we? Since we do have friction, it becomes what? All right. You're going to say this right here. Mg, my bad. I was looking at the one without friction. So it's going to be minus what? Mu k mg cosine theta. Remember I said that it will, right? Then it becomes what? Okay? All right. Yeah. So you solve it now. We're running out of time. I'm going to show you how to finish this up. I'll show you how to finish this up. Watch. One other thing we got to do. All right? So is friction opposing? Frictional force is which way? If it's going up, frictional force is also that way, isn't it? I'm sorry, y'all. All right, now watch. But now wait a minute. We got two boxes. We don't have one. But let me ask you something. The equation's going to be different? No. All right, let's think algebraically. In other words, I'm going to have to duplicate this again. So we got mg2, mg2, same thing, 3 and 3. Let me ask you something. Could I factor out the mass and just say 2 plus 3 and 2 plus 3 and 2 plus 3? Instead of having an equation that's 4 feet long. So you've got two boxes, not one. That's just for one. You duplicate that for the second one. So instead of doing all that, just factor out like terms and just say 2 plus 3 times all that minus 2 plus 3 times all of that, 2 plus 3. Okay? See if you don't come to an answer of 39.5 newtons. See if you don't come to that. You don't have one box, you got two. Now, like I said a minute ago, the only time we use the mg cosine theta is when we have friction. And I apologize, I was looking at my notes, and my notes on the problem I was looking at did not have friction. Okay? So basically, I could give you the same problem two different ways. Okay? Okay. All right? All right, see if you come to 39.5. Okay? And we'll double check this first thing Monday. Please bring everything, and we will